Hi, I'm John White, filling in for John Green, and you're watching Crash Course Pre-Chem. Today we'll explain how to name chemicals and write formulas, which I know sounds boring. Trust me, it is.
Ooh, Mr. White, but I love chemistry.
Shut up, me from the past who doesn't even look like me and is way too enthusiastic about school. Jeez. Alright, well, we'll try to lighten the load with cool props, bad editing, a lot of actual Crash Course references, and awkward scripts. But we have a cool theme song.
This is how you write the formulas for ionic compounds. First, you might want to get rid of that. Okay, so let's say a good example would be beryllium carbonide. So first you have to get the elements. This is too dirty. Okay, beryllium carbonide. So first you want to write down the elements. Yep, there we go. And you want to find how many electrons each one has. So beryllium has 2, and carbon has 4. So what you do next is you swap and drop. So you put them both back down here, and you just swap the elements. So 2 goes there and 4 goes there. And wow, look at that. You have an answer. But also you can simplify this, just normal math simplifying stuff, I don't have to explain it, into that. Because this is saying that you need 4 beryllium for each carbon, so you could just have 2 beryllium for 1 carbon, and that's the bell. So we obviously ran out of time at school, so here we are, last minute, Saturday morning, finishing up our project. Anyways, as I was saying, beryllium carbonide. Once you do swap and drop, you end up with this, Be4C2, which you can simplify to Be2C, because what this is saying is that you need 4 beryllium to go with 2 carbons. So, you just do some math and you end up with this. So, and how you would find out the name of a formula, if you saw it, is this, for example. You just say beryllium carbonide. You just say the elements and you add "ide" to the end of the second one. So that's pretty simple. And it's also good to note that whenever you only have one of something, you just don't worry about writing it because it's an understood one.
There's a void in my life. I need one more electron. Just one more. Look at this. 7. 1, 2, 3, 4, 5, 6, 7. One more. Anyone please. One more electron.
Oh, hey, bud.
Please.
Did you say you need 1 electron?
Yes, I do.
What a coincidence.
Oh,
I need to give 1 away.
Yes.
Whoa.
Yes.
Hey, here you go.
Thank you.
Wow.
Bless you, kind
Hey.
sir. Thank you. My life is complete now.
Hey, stranger, wanna buy some electrons?
Yeah, sure.
$20.
Alright, man. Oh, yeah. That's where it's at. Woo!
So now we're going to talk about covalent bonds. But first of all, what even makes up covalent bonds? Covalent bonds form when 2 or more nonmetals form together. So, for example, like hydrogen and oxygen, they're both nonmetals, so that's covalent. And when they combine, they make water. So I should probably write that up here. Hydrogen and oxygen. And I should also mention that covalent bonds, the way they actually bond is they share electrons. So, ionic, they kind of give them away, and this one, the 2 atoms are sharing. Yeah. So, we will, I will show this, like how this works, the magic.
So, for a more visual representation of this covalent bond, we have one oxygen and two hydrogens. And hydrogen, they both have one electron. And so oxygen needs two more electrons, and these both need two to complete their outer shell. So that means that they both have something that each other wants. So when they bond, they can share them just like this. So they come together, and as you can see, oxygen now has Oxygen now has 8 on its outer shell, and hydrogen has 2. So now they're all complete and whole, and they are bonded together and sharing electrons.
Okay, so writing out covalent compounds, like the names of them, involves the use of Greek prefixes. And they will be listed by the other thought bubble.
Alright, so when you form a covalent bond, the names depend on prefixes. 1 for mono, 2 for di, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa, 7 hepta, 8 octa, 9 nona,
It's nana.
and 10 deca. A very important thing to remember is that if the first element you write has only one atom, then you don't put mono.
Whatever. The second element uses all the prefixes. So, example again with H2O. Do that one. That's a 2. This one, I mean, you already know the name, but I'll show you why. So hydrogen has 2, so if you look back at that table, the prefix for 2 is di. So this would be dihydrogen. And the O for oxygen has nothing, so it's known as 1. And since it only has 1, the prefix, if you look in the table, is mono. So that is monoxide. And yeah, that's how you name them. Man, I have 4 electrons. I wish I had 4 more.
Man, would anybody want to share a couple of electrons with me and my brother here?
Oh, yeah, man.
Wait, really? You have a couple of electrons?
Yeah, I have a few I can share.
Really? Me and my brother Oxygen here, we really need some. That would be awesome.
Yeah, bro.
Okay,
So we
let's
can share
do
right
that.
here.
Okay.
Alright, hey, look
And
at
then-
that.
Hey.
Hey, we're like complete right now.
Whoa, this is
Well,
really
let's
cool.
Let's get in for a family photo. Family.
Hey.
Hey, John White back here. So thanks to my handy thought bubbles, they've explained the basics of chemical writing and formula writing and chemical naming, whatever it is. You know, get mixed around with that. But right now I'm going to explain polyatomics. So that might sound like a big word right now, but if you break it down, it's really self-explanatory because poly meaning many, then atomic atoms, and then there are ions that have different numbers of electrons. So from their original state. So polyatomics. There are a lot of different polyatomics, and they have kind of weird names. Ammonium you might know that one. Ammonium, bicarbonate, bisulfate, bisulfite, bromate, bromite, carbonite, chloride, all that. So if you notice, a lot of them are 8s and ites, and obviously I have not remembered this because I'm looking away from the camera and into this. That's why we have trusty charts, because we're humans and we don't want to remember things. So I'm going to put my trusty chart right there. And so now I'm going to give an example of a polyatomic formula with a transition metal. So we're going to use iron, Fe, which has a oxidation number of 3+. So 3+ right there, that's a plus, not implication. And then we have a polyatomic, we're using carbonate, CO3. So CO3, which has an oxidation number of 2-. So to understand polyatomics, they are combined and they're different atoms, but they still count as one unit in our formula writing. So you can think about it, sometimes you'll have parentheses around them, but we can just do that just so you understand it. So that's one unit, and we have. So after this, when you're gonna form them together, you're gonna do the same exact thing, swap and drop.
So the next step in the process, you're gonna swap and drop just like usual. So you're gonna go to iron. This 2 minus is gonna go down to there. So that's Fe2. And then this 3 is gonna go down to CO3. But guess what? So you think maybe, okay, we already have a 3 there, so I don't need to put it down there. Not true. You do need to put it down there. So you're going to put these parentheses like I was talking about earlier, and you're going to put the 3 right outside of those. So now, that's the formula. And yeah. So now, if you want to name it, what you're going to do is you'll have, obviously you start Fe and go into iron. Now, the thing about iron is on the periodic table in a section called transition metals, which means that when you write the name of a transition metal, you have to put the valence electron, you have to put the oxidation number in parentheses around it in Roman numerals. So iron, the oxidation number is 3+. We already know that. So when you write iron, you're going to have to put parentheses 1, 2, 3, like that. And then you're going to put carbonate. Notice that it's not carbonide like we had earlier with the other ionic formulas. So iron 3 carbonate is your final answer. Woo. Yep. Ooh, Stan, is it time for the open letter already? Let's see what the secret compartment has for us. Oh look, it's an electron. Thanks, secret compartment. Yeah. An open letter to electrons. Electrons, why you gotta be so negative? You're always running around getting attention? You're at the center of everything. Not really, because the nucleus is at the center of everything. But you have the most important part in reactions and formulas and naming, you divas. But keep doing you, because without you, we're nothing. I love you, electrons. Best wishes, John White. So in conclusion, we hope that we've been able to teach you these necessary skills that will definitely help you every single day the rest of your life. Also, in the wise words of L. Lissitzky, we believe that the elements in the chemical formula of our creative work, problem, invention, and art correspond to the challenges of our age. Ponder that for a second. Oh, and one more thing, a word of advice. Don't trust atoms, they make up everything. Today's episode of Crash Course was directed and produced by Lucas Sheppard, John Howard White, Dana McNutt, and Trey Butler. Our editing team was Lucas Sheppard and Tyler Wendt. If you have any questions or concerns, please ask our professional chemist. Probably won't know the answer. It's okay. We might. So thanks for watching, and as they say in John Green's hometown, don't forget to be awesome.